Hi everyone, last part of carboxylic acids is just to review all the reactions because there's so many, but they are really dictated by a similar kind of mechanism, which is addition and elimination. So here's our carboxylic acid, and here are all the derivatives. And so you should first know how this reactivity goes in order from acid chlorides to anhydrides, esters, amides, and nitrile, okay? And most reactive to least reactive because of the ability of the leaving group to leave, all right? Then you should sort of just start somewhere, like with one functional group, and just know how that reacts. You know, how do I start with this and make an anhydride? How do I make an ester? How do I make an amide? Okay, because it's pretty easy to go from here to here, and because this is the most reactive, all you need is love. First of all, it's the Beatles, and the second thing is what is the group that you're trying to replace, right? So that will pretty much tell you what nucleophile you need. And this one says pyridine because it needs to get the H off of there so that the O will attack. Okay, so just work through this map and work through how I can just do that. Okay, what do I need to do that? And maybe for this last one, we, let's see, from here to here, you guys learned how to also go from the anhydride to here to here. Okay, this one we didn't learn so much, so I wouldn't worry too much about this last one here, but you could probably figure it out if you had the time, but it's okay, just work on the ones that we explicitly went over. All right, now from here, you can also go to here and to here, okay, so you can think about all the different nucleophiles you would need, and also don't forget to make carboxylic acids also. You could definitely go to there as well. Okay, so take each functional group and really just look at it as a focal point. Okay, so here's one, and just look at all the different ways that it can react. So how does it turn into this? How does it turn into that? Okay, and you'll find out that a lot of these mechanisms are nucleophilic addition to the carbonyl. In addition to that, you also have reduction reactions, which are nucleophilic additions to carbonyl. So it's basically very similar, okay? The ones that are different are the oxidations. So oxidations, you just need to learn, are the reverse of the reduction, but they don't follow the same mechanism. All right, after you do that, so then take the next one, okay? So let's now start with anhydrides. So anhydrides, you can use water to get them here. You can use alcohol to get them there. Amines to get them there. But then once you go down the ladder, that makes it easy, okay? Going in one direction, starting here. How do I get to there? How do I get to there? All right, how do I get to there? But how would I go backwards? How would I get back up the ladder? So that's where it's going to be a little more challenging because there is no arrow going this way. All right, so notice it always goes down the ladder, but it's very difficult to go up. So that's where that idea from the first part of this packet came from, part 2 of the carboxylic acids packet, is that if you want to go backwards, you actually have to go through here and then go through there, or go up here and then go through here and then go to there. Okay, so there's this idea that you can from here make the acid chloride, and then from the acid chloride you can go anywhere, right? So that's sort of the idea that you want to, too many arrows, sorry. Okay, that's the idea you want to have is, okay, it's easy to flow downstream. Okay, I could definitely do that, no problem. But if I want to go back upstream, okay, I have to maybe starting with here. Okay, how do I go from here to here? Well, use the map. You know, we can go to here by hydrolysis, and then we could go to here, and then of course from here or here you can go anywhere, basically. All right, so work on making those connections, but it starts with just one simple thing at a time. Just, you know, how do these react? How do these react? How do these react? Look at the pattern. They all react pretty similarly. But then when you try to go from one down here back up here, you got to go through this this intermediate here, okay? All right, so then that's because, you know, these aren't as reactive down here, so you really have to convert them to something more reactive. So this map, I would expect you to know everything on here, maybe except this one thing over here, okay? So that will maybe be a bonus problem, or maybe it'll be something else. You don't need to worry about it, okay? Maybe if you just know all the rest of these, which we have gone over, and also maybe this one we haven't gone over as much, okay? So maybe I would just omit those two for now, and we've done everything else on here. Okay, so again, the idea is take something reactive, and you can go to all of these groups from there, all right? And just know what it is you have to add, because I might ask you, what's the reagent you need to do this? Okay, the rest of these are just practice problems. Happy to go over them with you and NMR practice as well. So if you feel like you've got those, that's great. You can stop the video and just review for your exam. But if you'd like me to continue and work these out and talk to you about them, that's what I'll do right now. All right, but before you move on though, what I really recommend for you is, besides going through all these reactions, is just practicing some mechanism till you feel really comfortable. I might pick any two of these and just say, you're going from here to here, show me the mechanism for that from scratch. Okay, so be prepared for that kind of a thing, all right? And you should know that for, you know, for hydrides, you can just use H- if you want as a shortcut. That's totally fine. For most of these, that's sufficient to figuring out the answer. And then oxidations, we haven't learned the mechanisms for those, so don't worry about those. But everything else you should be able to do the mechanism for. All right, so now I'm just going to go over problem after problem and talk you through it in case you're lost, things that you can think about. Here we're going to start with problem 32 from an older edition. Identify reagents to accomplish these transformations. So the idea with these is that you can use this reaction map to figure it out until you feel confident on your own to be able to do these. But I think you will see that at the beginning there's a really common theme, which is what I said, you know, when you're at an ester and you're going to a chloride, you need to go backwards in the ladder. So to do that, I would convert to a carboxylic acid and then to the acid chloride. So I'm thinking in my mind, I will do something like this, and then I will make it into that. So step one would be hydrolysis in acid and water, and then the last one will be thionyl chloride. Okay, so really simple. The next one is, okay, thinking about maybe making this into an amide and then reducing it. I know if there was a C double bond O here, we could reduce it with LAH down to here. So how would I do that? Probably, you know, looking at our ladder, we see that it's maybe not so easy to go from here to here, right? Because if I had an amine or ammonia, it would attack the H, not the carbonyl group. So maybe I'll just start off by making this and then make that. Okay, so for here, I will start off by making the acid chloride, and then from there I'll make the amide. So I'm just going to put R instead of the cyclohexyl group. Hope you don't mind. And then from here I can go to there. So the idea is step one, thionyl chloride, SOCl2. Step two will be ammonia, which will attack here and release the chlorine and do protonate. And then step four is excess LA. Step three is excess LAH, just to reduce it all the way down, and then water workup. All right. Okay. The third one, if you have not gone over these yet though, go ahead and pause it or stop the video and try these on your own. Try to use the map and figure it out, okay? And then come back to here if you want to see how we worked it out. All right, for this one, we're going from an anhydride to an acid chloride. So going less reactive to more reactive. So it's not spontaneous. I have to go backwards, right? So in going backwards, there is no arrow going that way, right? So maybe I think about going from here to here. Okay, so I'll just need some water, and that will attack here and release one of these, and I'll make a carboxylic acid. And then from my carboxylic acid, I can make that using thionyl chloride. Okay, next one, again, same idea here as with part B. I want to make the amide, and then from the amide I can reduce it down to the amine. So how do I make an amide? There's different ways you can do that. The one I'm thinking about is making this into carboxylic acid, and then same thing as I did in part B. Okay, so once you get carboxylic acid, then you can do the acid chloride, and then the amide, and then the amine. Okay, so how do I do this first step though? I just need to hydrolyze this. So acid, H plus in water, or H3O plus is fine. All right, this last one, we didn't focus on making nitrile groups, but you can do that from an amide if you use thionyl chloride. So that's a reaction we haven't done, so I would not worry about that one too much. This one here is acid anhydride to carboxylic acid. I just need to get rid of this with an OH group, so I can use water, or you could use sodium hydroxide, but you don't need something so strong. This is very reactive to water. This one here, this is very reactive as well. I just need to find a nucleophile with this in it, and ethanol is fine. Again, you could use sodium ethoxide, but ethanol will work just fine because this is so reactive. This amide gets reduced with one equivalent of hydride, so I'll use diol H for that. That will give me just one hydride to attack there. Another way to write diol H is to, I think it's down here somewhere, right here. This is similar to diol H, just a OR3H, so it gives you one H to work with. Okay, and then down here, this is something we did learn. You can hydrolyze a cyano group or a nitrile group into a carboxylic acid, and then from here you can reduce it. So to do that, we just need hydrolysis, so acid and water. We'll just get rid of this nitrogen as an ammonia. And then step 2 will be LAH, but you have to say excess, because we need to hit it twice to get rid of this double bond OOH. And then you're going to do water workup to make sure that's protonated and neutral at the end. Okay, and we're not too concerned with making nitriles. Like I said, I would maybe skip E and skip this one for now. Okay, so that's basically it. If you feel like you understood that, great, and work out the mechanisms and make sure you really know them. The key, I think, is understanding the order of reactivity here. This part right here. Okay, so know that order of reactivity and how to jump around, to carboxylic acids, to aldehydes, to alcohols, to amines, all right, as you can, okay? Just do one at a time till you understand it, and your brain will naturally make those connections, I think. Okay, and finally our last problem, spectroscopy. A lot of different carboxylic acids, and we're just reviewing some things about NMR. So go ahead and take a look at this for a few minutes and see if you can solve some of these. I'll call this A, B, C, D, E, F, G, H. Whoa, it's a lot. Okay, see if you can figure out which letter goes with which spectrum, and it's a lot here. Okay, so for this one, I'm noticing first the different functional groups. This is an aldehyde. Usually it's 9 to 10 ppm. Okay, so I can pretty much just look for my aldehyde. I only have one of them, so this has to be G. And if you look at the structure and the splitting and all that, should be able to tell that this works because, oh wait, sorry, this is past 10. This is a carboxylic acid. Okay, so it helps to know some of the peaks out here past the aromatic region. So if you recall, aldehyde H's were 9 to 10 generally, if you are able to observe them. And carboxylic acids are even greater due to the extra oxygen, the deshielding from that. So we have about 11 to 12 ppm for those in general. Okay, so this looks like a carboxylic acid of some kind. We have a doublet, so that's probably from some kind of a dimethyl splitting pattern where these hydrogens are split. The signal here is split by this, so it makes it into a doublet, so N+1. So that tells me that of the carboxylic acids here, it's probably A because of this dimethyl pattern. Okay, making that a doublet right here, doublet. That means the multiplet is the signal for this hydrogen split by all of its neighbors, 7 neighbors. So it's probably got, or sorry, 1, 2, 3, 4, 5, 6. 6 neighbors, so it's a septet, okay? So 7 peaks here, which maybe you can see 1, 2, 3, 4, 5, 6, 7. All right, this one here, okay, nothing past 3, okay, so not aromatic, which you would see at 7 to 8. This one I'm seeing triplet and a quartet. If you guys remember that pattern from last quarter, that's usually from an ethyl group, a CH2CH3. Okay, so probably have an ethyl of some kind, and then this between 2 and 3 is usually the alpha carbon of a carbonyl group. So I have some kind of hydrogens on this carbon. I don't know how many I have there. The integrations are not provided, but let's take a look here. So I've got ethyl group, so maybe like right here, but I don't see the OH here. I also have an ethyl group right here, but I don't see this H. But I see an ethyl group here, and I see an alpha hydrogen right here. So this is likely to be H. Okay, the next one, it's another doublet, so I'm thinking it's maybe a geminal methyl group. So I've got a hydrogen here splitting these guys' signals, and then its signal itself is that. So that's all I have though. So looking up here, I see E maybe, or maybe I see C. See, E would have another peak for this methyl group right here, but here this is all I have, so that must be C. Right here, 7 to 8, that looks aromatic, but this is weird because it's just a singlet there, and I don't have any aromatics. Okay, so it must be just super deshielded. Okay, or it might be some kind of variable group, like a H on an O or H on an N could be. Okay, all right, so let's look at this. This is a triplet down here. This is a multiplet. This is another triplet right here. All right, so I'm thinking that might be one of those variables, so something like that. But see, the OH groups that I already have, they're part of the carboxylic acid, so they should be down here. So other than that, I don't really have any H's on any O's, but I do have H's here. So now let's see what this pattern is. 1, 2, 3. That's a propyl group. Okay, so I'm guessing that's probably what we have here. So 1, 2, 3, NH2. So these N's are probably, these H's are probably there. And then this has 2 neighbors, so this will be a triplet. This will be a multiplet, and this will be a triplet. So that looks like this compound here. This is D. Okay. And then the last one is just this plain peak here. Just looks like a between 2 and 3 is usually downfield due to like an alpha carbon of a carbonyl. So it could be this. It doesn't have to be methyl, it could be ethyl. And then that's all I have. So it's highly symmetric. So just one kind, probably F then, because I only have the alpha hydrogens and they're all equivalent, so they'd be a singlet. Yeah, that's about all it could be. Okay, so here we go. Oh, there's more. Okay, so here, carboxylic acid. This one is a triplet. This is a quartet. 1, 2, 3, 4. Okay, so quartet and a triplet. Carboxylic acid with a quartet and a triplet. Now remember, our quartet triplet pattern was an ethyl group, so I'm seeing that right here. So that looks like B, and it's the only, I think it's the only carboxylic acid left. Okay, and this one, another doublet, and we have a single peak here, 3 to 4. Usually that's in the oxygen, carbon. It's the hydrogen's next to, on a carbon next to an oxygen, usually between 3 and 4. Okay, so I'm thinking ester probably. We have a multiplet and we have a doublet. So some kind of an ester where I would have a doublet. Here's an ester with the iso pattern right here. So, okay, the geminal dimethyl. This is probably it. So I've got my multiplet for this hydrogen and the doublet from here, and then a singlet from here. So that's E. And then this one is probably an aldehyde. It's from 9 to 10. It's an aldehyde with some splitting, so it's got some neighbors here. It's a triplet, so that tells me it's got 2 neighbors right here splitting it. So that's what I could tell from that end. Here I have a triplet, and I have maybe a multiplet. 1, 2, 3, 4, 5. Zoom in a little more. 1, 2, 3, 4. It looks like a quartet, but I can't tell for sure. Okay, so let's look at our aldehydes up here. So my aldehydes, I guess I only have one. So I just have this propanal, so G. So let's see if that fits. Propanal would look like 1, 2, 3. So my triplet is from there because it has 2 neighbors. And then this is my multiplet because it's getting split by the aldehyde hydrogen as well as the methyl hydrogens on the end. All right, perfect. Okay, so hopefully that will help you guys put all the pieces together for NMR. All right, on this one, we have compound A, and then it reacts with methanol to make compound B, and the NMR for compound B is below. So don't confuse this with compound A. It's the NMR for compound B. Now, here's the thing. This is a lot more complicated than it. Well, it's simpler than it looks. It looks complicated, but it's not. One thing that I can do here is I'm just thinking back to the reactions we've learned. And I know we have a carbonyl carbon probably, because we've been talking about reacting methanol with a carbonyl, right? So methanol would come in and attack. Now, I'm using this chlorine here as a clue that there are 2 chlorines. So it's very possible that one of them is right here, and that's the leaving group. Okay, so now that's just a hunch, and we're going to confirm it with the NMR, but that's the main idea. So if that's the case for compound A, then maybe I have a 4-carbon chain, 1, 2, and then I've got something else, right? So, we'll talk about that. But what if I have that and I have methanol? Okay, so here's methanol, and methanol will come in and it will attack there. And then this will come down and this will get lost, okay? So if that's the case, then I'm going to have OMe and some kind of group. So in my NMR for compound B, the product of this reaction, I'm going to have this methoxy group right here, and there's where my singlet comes from, and it's between 3 and 4 because of the deshielding from the oxygen. All right, well, now we have something to work with, okay, because I only have 4 more carbons. So either I have a straight chain 1, 2, 3, 4, or maybe I have a way of branching that. Now, in addition to these 2 ideas, I have to deal with the fact that there were 2 chlorines in the beginning. So I have 1 chlorine out here somewhere, and it's probably still on this chain. So if you look, different places I could put chlorine are here, here, or here, or here, or here, right? Which is the same as there. But look at the integrations as a hint. There is no methyl group remaining. See, there's no other 3H integration. So to me, that's telling me that I need to put a chlorine here. That way I have CH2, 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 which corresponds to these guys. Whereas here, if I put a Cl anywhere, I'm still going to have a methyl group to deal with. And so there is no methyl group based on the integration. Okay, so that means compound B is probably this methyl ester of this chloro substituted ketone, or ester, sorry, 1, 2, 3, 4. And the idea here is that these hydrogens correspond to there. These hydrogens, there's a triplet here that's sort of behind the singlet, but this is a triplet. And that would be from 2 neighbors. And this is between 3 and 4. It's de-shielded. Now these alpha hydrogens are usually between 2 and 3. So this is probably the de-shielded one. So I would say these are probably this triplet here. And it has 2 neighbors, which is why it's a triplet, 2 plus 1. These are probably a multiplet because it has multiple neighbors. These hydrogens are probably the ones right here. And then these hydrogens are between 2 and 3, and these would be a triplet because of its 2 neighbors. All right, so this is compound B then. And so what would compound A be? So just going back then, compound A would have had to come from this compound. All right, so just taking it step by step, and it really, the key to this was knowing my reactions. So knowing, what reacts with methanol? Some kind of carbonyl compound, and then going from there. Okay, last problem here. Provide reagents for these multi-step transformations. Go ahead and give these a try, and I'll go over these. All right, everyone, we're back. So I just jotted down some notes real quick. For this one, I'm thinking of hydrolyzing it to the carboxylic acid and then using thionyl chloride. Okay, so thinking back to our reaction map, remember this guy here? So if I want to go from here and I want to backtrack, okay, I need to go from here to there, okay? All right, so step 1 will be hydrolysis to the carboxylic acid. Step 2 will be thionyl chloride to the acid chloride. This next one is sort of tricky because you're adding a carbon. So the best way of doing that, I think, is a methyl Grignard. So we'll oxidize this to the aldehyde using PCC. Then we can add a methyl Grignard, MEMGBr, and water workup. Okay, and then once we get that, then I need to transform that functionality to this end carbon so that I can oxidize it there. So I'm thinking of doing acid dehydration. So dehydration, H3O plus and heat. So H2SO4 or something like that. Okay, so that will protonate this and it'll get lost and we'll do elimination. Or better reaction using Chem 262 would be convert this using thionyl chloride to Cl group and then do bulky base and get that. Otherwise, yeah, you can't really do it that way, can you? So otherwise it'll do the Zaitsev product. So what I want to do here instead is actually step 4, thionyl chloride, make this into a Cl, and then make that into a double bond, external double bond, like that. Okay, so more steps. Okay, this sounds sort of crazy. I wouldn't expect you all to be able to do this one without reviewing last quarter too much. I don't want you to have to do that too much right now, but it is coming eventually. So KOTBU and heat, we'll put the double bond here, Hoffman product. Then we don't want to do cleavage because you want to keep all these carbons. So we need to add an OH group on the end. So we're going to do anti-Markovnikov addition of water using our usual reagents for that. And then we're going to oxidize it using Jones. because at that point we'll have an OH group on this end, and we're going to have to oxidize it to a carboxylic acid. All right, so that one is, wow, it looks so simple, but, but it's not, right? It's a lot of steps. Okay, this one here, hoping you remember this oxidative oxidation at this benzylic carbon with KMnO4 or Jones reagent or sodium dichromate or any of those ones that does oxidation. Okay, except PCC, not strong enough. After that, we can make the acid chloride with thionyl chloride and then add this alcohol, propanol, 1, 2, 3, 4, OH, sorry, 1, 2, 3, OH. Or you can do esterification here, so just acid and propanol. Okay, either one's fine. Okay, so again, this one's less steps, but this one you might get a higher yield. Okay, and then our very last problem, if you want to try this one, is just to take, it's a kind of a reaction tree. Take a cyclic ester and just review all the reactions that we've had. We've had all of them except for this one. So just see if you can figure out what our products would be. And this is tricky because it's cyclic. It does open up, and so you're going to have to use the mechanism to try to figure out what you get. All right, for this first one, remember you protonate it and then water attacks here. And what's going to happen is it's going to open, come back down and open this up, okay, eventually. So what we'll get is, we'll get hydrolysis, carboxylic acid, but this O in the ring remains on the skeleton here. And then just want to count and make sure, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, I have too many carbons, so need to fix that. Okay, but it's good to make sure 1, 2, 3, 4, 5, and then the OH. And yeah, that's it. Make sure your methyl group is on the correct carbon. I think I have mine wrong here. See? All right, a lot of mistakes. All right, there we go. Okay, and another technique is just to label, you know, like that. 1, 2, 3, 4, 5. Okay. All right. Next one would be thionyl chloride. And thionyl chloride, through the same mechanism as for carboxylic acids, will give us an acid chloride like that. Okay. So for that one, you could probably picture that these would come in, and then this would attack, and then we would lose one of the CLs, and then the CL could come back later. All right, for methyl magnesium bromide, pretty simple one, just like that. And then eventually this will come back down and this will get kicked out. So we'll end up with a methyl group there. And then after acid workup, then we get this H. Okay, skipping this one for now, we're going to do hydride. So hydride will make this into an aldehyde at first, because instead of a methyl, it'll be a hydrogen that attacks. But do you guys know what the final product should be? Well, usually we assume excess if it doesn't say. Especially something as reactive as LAH, it'll just come back and attack again. So you'll actually end up with an alcohol here. Dibol H will be able to stop it out the aldehyde. So just deliver one equivalent of hydride. And NABH4 is too mild, so it only works really for very reactive, aldehydes and ketones, and very reactive. It reacts with aldehydes, ketones, and more reactive derivatives like anhydrides and acid anhydrides and acid chlorides and things like that. Okay, so that's when it would react, but an ester is just not reactive enough. And our last one is methanol in hydroxide. So hydroxide will deprotonate, and you'll end up with the methoxide. And the methoxide will attack, and you'll get transesterification. You get a different ester from this ester. So it should look like that. All right, so that's from this attacking here. and doing the same reaction as with all of these. Okay, so good luck with these. Just again, think back to your chart here. Okay, don't think about memorizing it, just think about understanding it. Okay, like first know the reactivity goes in this order, more or less. How to transform things the other way would be to go through an intermediate. And then think about oxidation and reduction reactions that you've learned as well. Those are really the main reactions I'm going to be asking you about. And then anything else that you can review or use from 261, 262 is great, but it's not like going to be a major focus for me. For me, I just want you to understand aldehydes, ketones, and these derivatives. So focus on the new stuff, and we'll review the old stuff as we can. Okay? Good luck, everybody.